I can turn it on using the other computer, but you guys have to wave your hands big time in order to catch my attention there on the screen if you want to ask a question. Sorry about that. I think I just need to restart the computer and it will be back, but I don't want to do that right now. Okay, so if that's okay with everybody, let me just start with some exercises that you can do for the background field method. If you like to do exercises about this, these are both fun ones. I like these myself. These are both in the new edition of our Dynamics of the Standard Model book. The first one is the instability in the Higgs potential. As a function of the Higgs part. And the Higgs potential has, in addition to the usual mu squared, phi squared, and lambda phi to the fourth, there's things that come from loop effects that have logs in them. And these logs with the top quark loop, so it's basically things that look like it's like phi to the fourth, the top quark loop, but there's a log also. These guys destabilize it. They have the opposite sign, and as the Higgs gets very big, I have to explain some notation first. The log gets big, and makes the potential turn over. And you can actually calculate the important part in a very simple way. It's trivial, essentially, if you use background field method. And then the basic point is right here, is if you know that the Higgs and then the top coupling goes like that. And so if you just define that the background field to be H is V plus H, and you're not worried about derivatives on the Higgs field, all you have to do is you have to calculate, which is basically a vacuum loop, the vacuum expectation value of T mu gives you the energy associated with it. And you just do a loop of tops in this background Higgs field where you just use the mass of the top as the function of the field. Then you just do this very simple diagram here. You get a piece that normalizes. So here's that guy goes like H to the fourth. This guy renormalizes lambda, and this guy here gives you the dangerous part of the Higgs potential. So it's a very, very simple calculation in the background field method. The second one is basically the same trick. This is Higgs production of Higgs K. One of the decays is Higgs to two gammas, or the production is gamma glue goes to Higgs, and the gamma doesn't couple to the Higgs directly, so it couples mainly to the top quark, and the easiest way to, okay guys, I see you just came back. I just explained these exercises. One is the instability in the Higgs potential, and the other is Higgs to two photon decay, or two gluons going to Higgs, both calculated in the same simple way here. And in fact, we can calculate two gluons going to two Higgs. Three Higgs all at the same time.
John,
Again,
there's
an approximation here. We're not interested in derivatives on the Higgs field or momentum factors for the Higgs.
Oh my God.
So this is valid when M Higgs is much less than M top. So we're not quite really there, but maybe 4 M top. But the trick of doing the calculation is so simple you don't have to do anything. And basically, you're interested in the two-photon coupling. So again, you use this background field representation. You take the vacuum polarization diagram for a top. And you get a log m top squared in that normally, follow the usual stuff. But now it's m top as a function of the Higgs.
Like an 80s music video. Let them know.
And then that gives you the Higgs coupling to two photons. Okay. And so if you go through the same exercise that we did for vacuum polarization, so this is gamma and gamma, you can get out, you can just read off the Lagrangian, which is log of m top squared, but this is log of gamma top v plus h squared. So you can read off the Higgs dependence of the photon coupling, and you get an effective Lagrangian that looks like this. This is actually for the blue one. Blue goes to Higgs. You do the Higgs two photon. The Higgs two photon is easy too. And you basically get this form, so the log m squared turns into log v plus h squared. And then this column here suggests that you show that there's a cancellation in the two Higgs production. And it goes basically like this.
Maybe it's just
the Higgs trilinear coupling. Those guys cancel exactly at threshold. And this thing tells you why two Higgs production by glue is suppressed in the standard model. This is the important factor experiment. So you can get that out with essentially no calculation. And what you've also done is you've done the diagrams for glue to 5 Higgs, 6 Higgs, everything comes out all at once. And I'm always impressed with ones like that. Okay, so that's, if you're interested in these techniques. Okay, okay. Dartmouth guys, you got my attention.
Your mic is on.
There we go. Now it's good.
Okay.
I think we're good now.
You hear me now?
Yes. Yeah, that's good.
Okay.
Wait.
Okay.
Wait, did you just turn on both? Yeah, only turn on one.
Good.
Okay.
Okay. Good. So now on to the heat kernel. This is mostly heat kernel day. So let's first do some general comments. Then I'll do a calculation. So heat kernel, let's define K of X, Y, tau, and some differential operator as X, e to the minus tau differential operator, Y. That's the heat kernel in most generality. It satisfies the following. Satisfies. If I take d by d tau plus d, I'll put a little x on it because it's at position x, on k of x, y, tau, d, that equals 0. And if you take tau goes to 0, that's if the exponential becomes just the unity. So if you have k of x, y, 0, d, that's just normalized whatever dimension you're working in. dd of x.
dd of x minus 1.
Okay, so that's the
Okay,
initial
so that's the
condition.
initial condition.
The
Totally.
name comes from
the following. So
if
d is minus alpha del squared, then and this alpha is the coefficient of heat diffusion. Okay, then this describes the diffusion of heat. So it's like the Green's function for the heat equation. And then it's then been explored. So the name comes from, so the history of it basically, it goes back to the 1800s, back when heat was a major topic, and there's an enormous math literature. That's the good feature and the bad feature. The good feature is that almost all its properties are worked out by mathematicians, and you don't have to do as much work. The bad feature is you have to dig through the math literature to figure it out. In physics, apparently, I didn't know about Fock that much, but apparently Fock was the first to do it. But Schwinger was the guy who really did it. Started it for QFT. Okay, and so you often see techniques based on this as Schwinger proper time. It's referred to as Schwinger proper time formalism, tau being the proper time. Okay. For gravity, it was used to great effect by Bryce DeWitt. And there's a bunch of references. There's a Seeley is the name associated with that. There's a great reference by Yoki, 1975. You can find that one in the reference section of the book. But there's a lot of generalizations of this. So we want you to do it with boundaries, without boundaries, do anything. We're just doing it in free space. So we got the easy job. Various easy things. Just if we have d is box plus m squared, we'll actually derive this as part of the next step there. It's k. Actually, I'm only going to derive in the coincidence limit, but the same. It's easy to see the derivation. If you have that guy, it's 1 over 4 pi tau to the d over 2. I'm doing this dimensionally. Well, it's actually any dimension. E to the minus x minus y squared over 4 tau plus tau m squared. And you'll actually see the derivation as I do the next step, basically, the free field things. This also lets us do the propagator. So, if you have I over, so let's call it just A plus I epsilon, you can write that as the integral 0 to infinity d tau e to the minus beta plus I tau A plus I epsilon. So it's just doing the simple integral. But this then let's just give it a definition of the propagator. If we have I, Feynman propagator of x minus y, that's the x, y representation of I over box plus m squared, I epsilon, y, and it's then 0 to infinity d tau. So when I exponentially box plus m squared, and I've got k already, I could basically be plugging in k. It's d tau over 16 pi squared tau squared. That's that part right there. And then I have e to the minus I x minus y squared over 4 tau squared, 4 tau plus tau m squared, tau m squared plus I epsilon.
Wait, sorry.
So there's a interesting representation of the propagator. It's a Schwinger trick.
What's tau?
Tau is just the proper time. It's just this variable.
So it has
Well, it's dimension whatever you use d for.
I was just true, but
Yeah.
to justify the first.
Yeah. So it's actually in m squared minus inverse
Okay.
inverse mass squared when d is a differential operator. I think it goes like box plus m squared. Okay. Okay. And this guy actually is probably the easiest path to the massless propagator. So if m is equal to 0, that's an easy integral to do then with m equals to 0. It's not easy in general. This turns into minus 1 over 4 pi squared, 1 over x minus y squared minus I. So there's the position space propagator for mass skip particle. Done this way.
Hey, what about the
Okay, so there's some of the general stuff. And so if you want to see some of this done in another field of theory context slightly different from what I'm doing, I know Max Schwartz's new book.
Yeah.
His QFT book has a section on using the Schwinger proper time representation. And what he does is Euler Heisenberg Lagrange and things like that. If you haven't seen that stuff, it's actually fun to read. Okay. So I'm going to use this to do a calculation. I'm going to do my favorite example, the photon vacuum polarization using the heat kernel. So gamma, and somebody propagating through the center there. Okay. So we're trying to make sense of trace log d mu plus m squared, where d mu is d mu plus I a mu. And this trace turns into integral d for x. So that's what that one means. And the log we're going to use for the heat kernel. So use log b over a. I gave this identity last time. Is integral 0 to infinity d tau over tau e to the minus tau A minus tau B.
So when we did the propagator, I just gave you the propagator was the tau without the tau downstairs. So now it's just a different power of tau. You get the log.
And so then I'm doing trace log d mu plus m squared. That turns into then integral d for x, integral 0 to infinity d tau x e to the minus tau d mu plus m squared x. So this is my heat kernel k of x and x. So it's just in tau. So the trick is now to just evaluate that. The way we're going to do it is we're going to use
No, I know, but like just using this formula. I thought we should have or should.
Let's use
So
completeness. I'm going to use momentum states. Px equals e to the p dot x. To rewrite this, and actually, by the way, I should just comment that in the notes from our book, we call this H for heat kernel. H. So either one. I have actually come to not like
to regret the fact that
we called it H because H is Hamiltonian, and so kernel better. So I'm going to try to use K, but my notes are all written for H. So you have to watch out. Anyway, so here we've got H, now K. Here we go. K of x and tau is now going to get rid of integral dp 2 pi to the d e to the minus I think p dot x e to the minus tau d e to the I p dot x by using this completeness to get the matrix sums in x and x matrix sums in terms of these plane waves. Then I use d mu e to the I p dot x is well the derivative on e to the I p dot x gives me the momentum back. So this is e to the I p dot x.
what happened to the other?
I p mu plus d mu. Okay. So if this is, I'm basically expanding this exponential. And anytime I see a d, the expansion expand in tau. Anytime I get a d derivative, I'm acting on this e to the I p dot x, I replace it like that. So then basically you just keep continuing d mu e to the I p dot x is e to the I p dot x I p mu plus d mu p mu plus d mu blah, blah, blah. And you then end up with k of x and tau
Where
is
Ron cut?
integral d dp 2 pi to the d,
Gets
e to the minus I tau I p mu plus d mu squared plus m squared, so I can basically re-expand it. And actually, this is where you would get the. I've used the diagonal one, so I've got both of these at x. But if I had x and y, I'd have an e to the I p dot x minus y here, and then there's a tau p squared sitting right there, and that's where I would get my free field representation. So basically, the thing I gave you up here, if I do what I did there and I do the p integral, I get this. Okay, so I actually don't have the full derivation here, but it's basically the p integration of this with the e to the I p squared.
Cycle with operators.
Okay. Okay, so there we've got that. So this guy over here, I'm going to write as e to the tau p squared minus m squared, and then e to the minus tau d mu plus 2I p mu d mu. Okay, p is just a number here, so the ordering doesn't matter. Okay, so that was easy. And then we expand k of x and tau is now integral d dp 2 pi to the d e to the tau p squared minus m squared 1 minus tau d mu plus tau squared over 2 d mu minus 4 p dot d p dot d. Then there's a tau cubed piece, which is d dot d p dot d p dot d. No, actually, I'm sorry. My handwriting fooled myself. P dot d p dot d p dot d plus dot dot. Again, let's not do all the ones. But I do just want to make the comment that you have to go up to tau to the fourth to get the answer right. There's a 16 tau to the fourth over 4 factorial p dot d p dot d p dot d p dot d.
Yeah.
Okay. The higher ones don't contribute to the order we're working, but all these guys do.
Right, he has that e to the tau p squared.
So
Hey, what
you see, at this stage there's guys that have 2 derivatives. There's guys that have up to 4 derivatives. The answer that we want to keep is up to 4. You'll see that in just a second. Okay. Then there's a bunch of simple, straightforward integrals. The p integrals have to be done. So there's either tau p to the tau p squared with exponential and powers p. And so you use things like the following. Here's, I'll give you a couple and I'll leave off the painful one.
Is it p when you do the dd over p integral?
To do this best, you want to take
And it kills it?
P into Euclidean P. So just make sure you got the notation right.
Yeah, exactly.
P1,
No, not one.
P2, P3
Second one is not in the.
minus I P0, P4, just to make it Euclidean. Because then it's just a spherically symmetric integral. So then you have d P Euclidean 2 pi to the d e to the minus P Euclidean, no, P Euclidean squared plus m squared is what times tau is what you're integrating. So that's the first term. And then you know how to do these, you break it up into the angular integrals because it's the d-dimensional angular integrals. And then a radial integral, P Euclidean, P E Euclidean to the d minus 1, e to the minus P Euclidean squared plus m squared tau. Here, this first factor turns into this is 2 pi to the d over 2. That's over gamma of d over 2. That's the thing you do dimensional regularization. You always get that. There's the 1 over 2 pi to the d and e to the minus m squared tau. Factors out, and then you get gamma of d over 2 over 2 pi to the d over 2. This ends up being 1 over 4 pi d over 2 e to the minus m squared tau over tau to the d over 2. Okay. And that's also something I gave you above that. This is again the piece that if I put a p to the minus I p dot x minus y, it gives me this result that I quoted up here. Here's 4 pi to tau d over 2. Here's the minus tau m squared piece that I quoted. And then this piece, if I had the Fourier transform e to the minus I p dot x minus y here, I've just completed the square, shifted, and I get that last piece.
Why are you doing an experiment?
Anyway, I should have done it straightforwardly out. Okay. The others follow similarly. If I have e to d p Euclidean 2 pi to the d, I won't do this one out. P Euclidean squared plus m squared tau P U P nu.
I have to take into account all orders anyway.
B Euclidean. Okay, so that's since it's, the rest of it's spherically symmetric, that comes out proportional to the delta mu nu, which is like eta mu nu, but in Euclidean. And there's just some other factors here over d 1 over 4 pi d over 2, 1 over tau d over 2 plus 1 e to the minus m tau m squared tau gamma of d over 2 plus 1 over gamma d over 2. Okay, and then there's one for the you need the 4 one, the 3 guy one vanishes. The 4 one is just a bunch of delta functions. It's called, it's in the book. In the book, look it up. Anyhow, this then just allows you to write the kernel in this case
tau is e to the minus m squared tau gets pulled out in the front over 4 pi d over 2. Tau is a d over 2, the first factor 1. In this case, but not in all cases, the linear piece vanishes.
Plus n.
And the next piece that comes out is 1/12 d nu d nu d nu d nu. Okay. So that comes from just collecting there's d squareds all at various places here, and you just write out all the possible d squared pieces and collect it. And then this has the tau squared with it. And then plus I. So there we go. But what is this? This is f mu nu, e f mu nu, and this guy is e f mu nu. Okay. And so then the last thing that you end up having to do is the tau integration. So we now have k in this tau expression. And then to get my final answer, all I have to do is integrate over tau. And so now the last integral is the integral 0 to infinity, the tau over tau is what we had. I have e to the minus m squared tau 4 pi d over 2. Tau squared is the interesting one there over tau to the d over 2. This is an easy integral, minus 1 over 4 pi d over 2. M squared to the d minus 4 over 2. Gamma of 2 minus d over 2. Okay. This then goes, you go back up here, and I now evaluated this. Gamma of 2 minus d over 2 is the traditional 1 over epsilon, which is 2 over 4 minus d. And then it gives them the renormalization. I've now got changing the Lagrangian is the integral d4x. I have got f mu nu e squared over 16 pi squared. 16 pi squared is 4 pi to the d over 2. 1/12 is the 1/12 from there. And then 2 over 4 minus d, the stuff that comes along. So this is the wave function renormalization that you get from calculating that Feynman diagram. But the thing that I find most interesting, or at least interesting about this, is that nowhere here did I do a Feynman diagram. Okay, if you think about it, there's no, you didn't see any inverse propagators. We didn't Feynman parameterize them. We didn't have to do the usual shifts of momentum variable. We didn't have to write out what the gauge variant form was going to be.
Right, it's in front of the F here and you're
So this is Feynman diagrams without Feynman diagrams.
so
It's a completely off the wall way of doing Feynman diagrams.
wait, so what?
Okay. So there's the example of how you can use this. And so it's great in the background field method. You take your field to the background field method, you do these tricks. Moreover, the mathematicians have done all the tricks for us. So let me just write out the general property. So in general, okay, so we have k of x and tau as x e to the minus tau some differential operator. I'm calling it O x, and we're going to expand this in terms in perturbation theory in terms of tau in the proper time, and it turns into I over 4 pi to d over 2 e to the minus tau m squared. That's always the case over tau d over 2, and then one expands a0 of x plus tau a1 of x plus tau squared a2 of x plus dot dot dot. And then depending on what the differential operator are, these kinds of forms that have been worked out. So for example, if the operator has the form d mu plus sigma, one we played with before with d mu being the derivative plus some gamma mu. Okay. And I guess I also should add in here plus m squared, sorry. I need to write m squared. Then in that case, a0 of x is 1. That's what we worked that one out already. It was just the expanding this thing. A1 of x is minus sigma. Okay, you can do that one in your head too. Because if it's sigma plus m squared, and we know we have e to the minus tau m squared, so it's really e to the minus tau sigma squared plus m squared. And the first expansion then is e to the minus tau sigma would be the first piece. That's easy. And the second piece you also get, if we can get the piece there, a2 of x, is you can get the sigma piece from that also. It's 1/2 sigma squared, and 1/12 d nu. Okay. That should look familiar from what we did before when we were doing the other way of doing background field method. And then 1/2 sigma squared again, just the expansion of the exponential. And then there's one more piece which we didn't find before, but which didn't. In general, it's d mu commuted with d mu sigma.
Okay, this guy turns into a total derivative when you do the integral d for x a2 of x, which is what we were doing. So we're taking the trace, some integrating over d for x. So that got turned into a total derivative, and so that was dropped in a previous calculation. But the heat kernel doesn't have to always be used in this particular context. It lives on its own. There's a piece of the heat kernel that's there. Okay, then we can do our trace log trick. And so these guys were found before. That was the piece before. And we have the integral d for x. Then you do the tau integration, and you have x log of this operator x. That turns into minus I over 4 pi d over 2, sum of n equals to 0 to infinity. The terms, there's a series, basically the tau series there. It becomes m to the d minus 2n gamma of n minus d over 2 integral d for x a n of x. Okay, so there we've done the general expression. What you see here is the divergence A2 contains the divergences of the theory. Okay, so the coefficient A2 that we did, we picked out the wave function normalization from A2. In quite generality, if you have any of these operators, what you want to do for normalization, just look at A2. Okay. At least when f is not equal to 0, then everything else is finite. So these A, N, and X have a name. They're the Seeley DeWitt coefficients. And they're tabulated for different theories. I'm going to give you the gravity theory rules, but I'm not going to do that. But there's the Gilkey 75 reference is a good one. Again, it's easy to locate. Certainly, it's in the back of our book. And I've also on the web page I've put a user manual. A preprint by Vasily Vasilyevich, which has a lot more information in case you ever, if you like this stuff, you can take a look at that. It's a little bit more mathematical than I want to be in the course, but that's the good thing. Vasilyevich. Gilkey. Now, to be honest, I never read the paper, but it's one of these papers where you see quoted all the time, and you see the quotes, another place to find a lot of this information is in the Burrell and Davies book, or Parker and Tom's.
It's basically all throughout the
field theory and curved space-time literature. You can't read that literature without these guys.
Okay, for gravity. Okay. I don't have a derivation for this, but here's, I think I have, in preparing for this, I think I have an easy way to do it. And the following method should work, but I have not done it. Okay. So, but here's basically the issue. Let's just slightly different differential operator. So the differential operator is that we have here is the integral d for x square root minus g. G mu nu, d mu phi, d nu phi. That's our Lagrangian for scalar. Imagine I'm trying to do that loop. Then this is going to be d for x. I integrate by parts. I get phi d mu square root of minus g, g mu d nu. So here's my differential operator. Maybe we can integrate these there. Now that doesn't fit our traditional pattern, but I think I can put it into the traditional pattern by the following. And I'm probably going to not do as much derivation as I thought, but here's a piece of useful gravity physics that I want to say at some stage in this class. Let me say it here. This is the use of Riemann normal coordinates. So this isn't a great aside anyhow, because these are a great way of thinking. So what you know is we can make things locally flat. So if we're in a little patch around the point x, I can make it flat at x, and the deviation from that is the overall curvature that goes quadratically. Now, Riemann normal coordinates is a way that puts this in the most generally covariant form that you can have. Let me imagine that I'm at the point x, and I'm using y is x prime minus x. So I'm looking around there. Okay. G mu nu and x prime then can be Taylor expanded around this. It'd be eta mu nu is the leading piece, and then anything else would be deviation. And the first deviation is a third r mu alpha nu beta y alpha y beta. So it's quadratic, and then there's y cubed in order to y to the fourth, which you can find. Okay, if you're interested in this, my reference in this is Burrell and Davies. But it's you probably Wikipedia, probably there.
the square root of minus g then is 1 minus a third
r alpha beta, y alpha, y beta. And the curvatures here are evaluated
at x, at the point x. Okay. Now, let me just mention a little bit about the derivation. And if you're interested in the, I'm doing lots of exercises today. A good exercise is to derive this, or is to show it's consistent. Is obtain r mu nu alpha beta in Riemann normal coordinates. Here's what you do. I actually have worked now, but basically, we know that gamma mu nu lambda starts off like 1/2 g mu g lambda sigma d mu g nu sigma plus dot dot dot. Okay, there's 3 terms in it. If you're using these coordinates, you can then get a representation of this, that the first guy here, if we're working to first order, the derivative has to act on the y's. So that's on those guys. So this first guy can be taken to be eta, the flat space. And then this, you end up showing that this is minus a third eta lambda sigma over 3. It's r mu alpha nu sigma r nu alpha nu sigma, symmetric in sigma, y alpha. Okay, so you take away one of the derivatives, one of the y's by taking a derivative in the first place. And you get that, and then you form r from derivatives of gamma and gamma squared. But gamma squared pieces out, drop out, you don't even need to calculate it, is the order y squared. The derivatives of gamma get rid of the other y, so d on the y alpha. And then you have to use the Bianchi identity. The Bianchi identity, one that I gave you, which is r mu nu alpha anti-symmetrized beta equals 0. Okay, you get a product of terms here, and you end up then rearranging them, and you get the right curvature out. Okay, so that's how you Taylor expand the metric in terms of curvature. All right. So using this, you can put this funny O into the d mu plus sigma form, and presumably, if you work it out, you get the answer, okay, in terms of these r's, because that's what the answer comes out. So you want the answer only involving the curvatures. So the Seeley DeWitt coefficients okay, for a scalar field, so that I would
Actually, I'm doing it for the Lagrangian is d mu phi plus m squared phi squared plus c r phi squared. Okay, if you remember, I did this earlier on when I was doing improved energy momentum tensors. So I had the results for the general case. C is equal to 0 is called minimally coupled, and C is equal to 1/6 is conformal, which I'll explain that more later. When we're doing anomalies, yeah. So in your case, if you're doing, are you doing Higgs inflation? Okay. Yeah, it'd be the conformal factor. There's, another thing could have been called, it'd be conformal coefficient probably. The conformal factor often is if you take G mu is e to the I, then e to the 2 sigma of x, this is of x, some G bar, that's, I would call that the conformal factor. So the rescaling of the metric. Okay. And we'll talk about that. Okay. In any case, this guy A1 is 1/6 minus C of curvature. Just there's no indices left over. A2 is it's 1 over 180. R mu alpha beta, R mu alpha beta minus R mu plus 5 halves 6c minus 1 squared R squared minus 6 box. So again, the box are, if I was putting this into a Lagrangian integrating over x, the box are the total derivative disappears, but the rest of these would stay. Okay. And again, it's nice to work it out there. It's worked out for all other cases too. So let me do photons. So if you have a photon, of course, your covariant derivative changes. So what you mean by the covariant derivative is different. And then A1 for the photon is 0. That's actually that's hard to get. A2 for the photon is minus 1 over 180. R mu alpha beta, R mu alpha beta, minus 86 R mu plus 20 R squared. And actually, in this case, I did take this from a place where I was using the Lagrangian. So I'm going to put question marks on it. I actually don't know the coefficient off the top of my head on that. Okay, but again, that's the total derivative. Okay. So
First terms cancel each other out. That's not so much. I mean,
so there's the answer is worked out in its own for spin and half and spin 2 even. I'll do spin 2 and gravitons. I'll show you. But let's do the following. I want to use this to interpret something that we've done. Let's go back. Let's go back. Here's a recall. we did.
I wrote out the Feynman rules for
the Feynman rules for gravity.
For example, I had P and P prime hooked up to gravity, which was
minus I kappa over 2 P mu P prime nu P prime mu P nu. And I showed you the result for doing this for a loop where the momentum Q coming in, nu, alpha beta Q going out, and I did the loop.
Okay, this has various features. It was order kappa squared because there's two of these guys, kappa and kappa. Because of the momentum factors, it ends up being Q mu, Q nu, Q alpha, Q beta, plus various other forms. But the main factor is it's of order Q to the fourth. And it also was divergent. It was 1 over epsilon plus dot 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 there. So to be precise, I have sitting down here at the bottom, I've got the notes. I'll shift this up later. This is notes from last time, or from earlier class. I think, let's see, it was February 12th. And so here's going through the vacuum polarization for gravitons and finding out we have something that goes like kappa to the fourth. Now we're sitting over here is the formula is nice and minuscule right now, but that's what it is. But the issue I left you with was this divergence. It has a divergence, but doesn't go into renormalization of the coupling constant because it has a different momentum factor, and it doesn't go into wave function renormalization for these guys. But now we see what it is. We now know how to do. We see this better using the heat kernel. Okay, so basically what we've done is we've got from our formula, say d4x, x log O x, we have this as being 1 over 16 pi squared, 1 over 180. We have integral d4x, square root of g comes along when I'm doing the trace. I've got r mu nu alpha beta, r mu nu alpha beta, minus r mu nu, plus 5 halves r squared. The calculation I showed you was minimally coupled, c is equal to 0. And then I have the 1 over epsilon bar piece that we get. And you can now see the structure, what it has to be. Remember, R and all these curvatures are like two derivatives on the fields. They start off with 2 derivatives on the field. So that if I have then r squared, it's of order q to the fourth when I take a matrix element. And so the heat kernel thing that I might represent like that. Here's the matrix element of that operator equals this when it, from doing the loop. And so this is the order h squared term that comes out of that. But the beauty of what we did is, here we've now done more. So the obvious comment is doing this calculation down here is extremely painful to get all that thing out. Whereas doing this one here is trivial. You just look up the coefficient from Gilkey, and you don't have to do any work at all. So one is easy. Two, we've also calculated all the other divergences in the theory all at once. So we've also got divergences that followed from that guy, from this diagram, plus this diagram, plus dot, dot, dot. We've got all divergences for all diagrams. No matter how many legs there are on it. This is impossible because they're constrained by general covariance. Well, general covariance was not at all obvious in the thing I showed you before, the field theory calculation. It's completely obvious here. And so, in fact, this is probably the biggest feature, is this technique makes the general covariance obvious. Okay, it was not obvious just during perturbation theory. And that's great news, because we'd like to do it. And then the fourth thing now we haven't gotten here, this also shows us how to renormalize. We have to generalize the Lagrangian, so the Lagrangian is going to be D4 for the action, D4x, 2 over kappa squared R, plus I'm going to need terms, C1 R mu alpha beta, plus C2 R mu nu, etc. And those are general covariant conditions of the action, and divergences go into renormalized coefficients there. Okay, so it's a great place to stop. I have a couple other things to do on using this heat kernel method.